Welcome to this quantum security and defense presentation, motivating recent advances in quantum LDPC codes. Asmae Benhemou is a PhD student at University College London in the Center for Doctoral Training in Quantum Technologies and will soon begin a postdoc at the Yale Quantum Institute. Her research focuses on quantum error correction, fault-tolerant quantum computing, and quantum simulation. She earned her master's in Physics and Astrophysics from the University of Glasgow in 2019, where she worked with an ion trapping group at the Institute for Quantum Computing in Waterloo. During her
Thank you. So this is the title of my talk. I'm going to be talking about specifically quantum LDPC codes as error correcting codes and why we're interested in them. This is a brief outline, so I'll just mention some basics of classical error correction and then motivate quantum error correction, talk a bit about LDPC codes and the challenges that we encounter, which motivate us. And then, there's one word missing, but I'll discuss a few experimental results recently that are also, quite exciting. Okay, so I'll start a bit about error correction. So the idea here is, we want to transmit some information across a channel. Inevitably, there will be some noise, and so we need some kind of error correcting protocol to, counter this noise. So in the classical case, you can expect, a bit flip, for example, as an error. So this will just take your 0 bit and flip it to a 1 and vice versa. So an example of a channel that applies this is the binary symmetric noise channel on the right over here, which flips a bit with a probability p. Essentially, the idea is you can counter this type of noise by adding redundancy to protect your information. So for example, you can use what's called a 3-bit repetition code or an n-bit repetition code. In this case, you basically define a map, which is going to map a, I think this is a bit better, second point. So you can map, your 0 to 3 copies of the 0 bit, the 1 bit to 3 copies of the 1 bit. And this defines a code space. So if the information that's been received is anything outside this code space, we know that an error occurred, and we can use some error correction technique to, if, for example, here's just a majority vote, we'll infer, okay, the message was supposed to be 111 or 000. This is not fallible. Well, this is fallible, sorry, it's not infallible because you're only protected up to a certain parameter, which is called the code distance. So specifically, if you have an NKD error correcting code, it's defined as a code space essentially. So it's a subset of F to N, which encodes K bits of logical information that you want to protect into N physical bits.
Thank you for watching this short intro. The full presentation, together with other lectures from quantum experts, is available on www.quantumsecuritydefense.com.